Calculating the wind loads can be challenging because there are many parameters and steps involved. In this video, we'll show how to calculate the wind loads on walls according to Eurocode, step by step. To do that, we use an example of an office building. If you like written content more, then you can also check out our article on our homepage. We'll leave a link in the description below. Alright, let's get started. Normally, we start off by calculating the peak velocity pressure. However, we already did that in our last video, as it is a topic for itself. You'll find a link to the video in the description below. In that video, we calculated that the peak velocity pressure of the office building is 0.75 kN per square meter. In general, Eurocode distinguishes between wind pressure on external and internal surfaces. This article is focusing on the wind pressure on external surfaces, as this is used for the overall stability of the building. So the formula to calculate the wind pressure on external surfaces is peak velocity pressure times external pressure coefficient. The coefficient CPE has two different values, depending on the wind loaded area. There is a value for a surface area of 1 square meter and 10 square meter. Now, you're probably wondering, when do we ever design a load-bearing element where only 1 square meter is loaded? Well, you're right. That is almost never the case for beams and slabs, or walls. But for smaller elements like cladding elements of facades or fixings, CPE 1 comes into play. Eurocode gives recommendations for values of CPE. This means that you have to double check with your national annex because those values might be defined differently there. Eurocode gives values of CPE for 5 different areas: A, B, C, D, and E of our building. The size of the areas depends on whether the wind comes from the front or the side. For our office building, we can define the geometrical parameters for wind from front as width of the building B equals 49.75 meters, length of the building D equals 20.2 meters, and the height of the building H equals 17.1 meter. From those dimensions, we can now define E, which determines the width of areas A and B. And E is calculated as the minimum of B and 2 times H. If we put in the values of those parameters, then E equals 34.4 meters. Alright, now let's visualize these areas in a floor plan. If the wind is coming from the front, then area A is located on both walls parallel to the wind direction, right behind the corner exposed to the wind load. The width of the area A is calculated as E divided by 5 equals 6.9 meters in our case. The width of the area B is found as D minus E divided by 5, which equals to 13.3 meters. Areas D and E have the width of the building. Now we would also need to do the same for the wind coming from the side. But let's rather jump into the wind load calculation. I think you understood how to calculate the wind load areas. But in case you want to see the wind load area calculation for wind coming from the side, then check out our written article. Alright, maybe you have already forgotten, but the wind load is calculated as peak velocity pressure times coefficient of the external pressure. The peak velocity pressure was calculated already in our last video as 0.75 kN per square meter. So we are basically missing the CPE values for areas A, B, C, and D. We find those values in Eurocode for a ratio of height divided by D equals 0.85, which is less than 1 but also greater than 0.25. So therefore, in a table in Eurocode, we find CPE A as minus 1.2, CPE B as minus 0.8, CPE D as 0.8, and CPE E as minus 0.5. Based on these coefficients, we can now calculate the wind pressure on external surfaces. For area A, we calculate the wind pressure as minus 0.9 kilonewton per square meter. For area B, we calculate the wind pressure as minus 0.6 kilonewton per square meter. For area D, 0.6 kilonewton per square meter. And for area E as minus 0.38 kilonewton per square meter. When you calculate the wind loads the first time ever, it might be very confusing in which direction you have to apply the loads. So let's apply the wind loads on our building together. Basically, the minus means that the load is facing away from the surface. The wind loads of areas A, B, and E are therefore facing away, and the wind load of area D is facing towards the facade surface. Lastly, according to Eurocode, the wind load in the wind direction can be reduced if the ratio height divided by D is smaller than 1. That is the case for our office building, and therefore we can reduce the loads of areas D and E with a factor of 0.85. So let's do that. The wind load of area D can be reduced to 0.51 kilonewton per square meter, and the wind load of area D can be reduced to minus 0.32 kilonewton per square meter. To summarize, for a building with a height of 17.1 meter in a suburban area in Copenhagen, Denmark, the wind load on walls is calculated for 4 different areas for 2 different directions. After this, the stability of the building can be verified. In our case, the concrete cores are transferring the horizontal loads to the foundation. Thanks for watching. If you enjoyed this video, please give it a like. And you can also find other structural engineering guides on our homepage, structuralbasics.com. Until next time.